All right, guys, welcome back to Coders Campus. This is going to be another assignment walkthrough video. The actual assignment that we have that was submitted was something to do with the binary tree data structure. So what I'm going to be building for you today is a representation of a binary tree data structure where you can add nodes, delete nodes, and traverse the tree. And we'll even, I can even show you a few ways that you can traverse the tree that are very popular. And we can take a look at all that. And so that's exactly what we're going to be doing. So let's jump right into it, shall we? So I'm going to go ahead and create a new package. I like to show, the students exactly how I go about doing all these steps, just because it's nice to see a project start essentially from its beginning point to its inception, if you will. So I'm going to create a new package, and I'm just going to call this one, tree, because there's several types of trees, but for this one, we're going to be creating a new class, and I'm going to call it a binary tree. Sound good? Now, if you wanted to, you can add a public static void main method, which would essentially turn this into a runnable Java application, but that causes some issues because it uses this keyword static, and I prefer to use something along the lines of testing. So I use something called JUnit to create test cases for my assignments and whatnot. So that's just what I do. So I won't use the public static void main, and I'll click on finish. So I've got my public class binary tree. Now, there's a few things that we need to understand about binary trees. Just like in our previous video where we talked about linked lists, the binary tree also has nodes. All right, and nodes, usually contain some sort of a key, which we refer to, usually as the data that exists inside of the node, and that's what we use to actually store the information. So that's the important part of each of these nodes. Now, another thing that you need to know about these nodes are that with respect to a binary tree specifically, you can only have two children. Okay, so there are only two children that a node can actually contain, and that is usually a left child and a right child. Okay, so at most, any given node can have two children. It can have 0 children, it can have 1 child, or it can have 2, but it cannot have anything more than that. So that's sort of the property of a binary tree. Okay, so how can we accomplish this particular data structure? Just like I did for the linked list, I'm not going to do it inside of the binary tree class itself. I'm going to create a node that represents this particular node, the binary tree node. So I'm going to right click on my tree, I'm going to say new class, and I'm just going to call this node. I could call it binary tree node, but that's just a lot more typing for me, so I'm just going to be lazy and call it a node. And inside of this node, as you saw in the binary tree, it needs some sort of data, and it needs 2 children. So the data that we're going to store in this one is probably just going to be an int. I'll call it data. And it's going to have a left and a right child. Now remember, the left child and the right child that are the children of the node, what are these things? What are these children? What is the data type? Because I need to create, a left child, but I need a data type, like I have int here. What's the data type going to be for this left child? Well, actually, it's just a node. Okay, so just like we had before in our linked list description, our linked list video, each node contains, for a linked list, each node contains a pointer to the next node, but for a tree structure, a binary tree, each node contains a pointer to a left child, which is a node, and a right child, which is another node. All right, so there we go. That's more or less what we're going to create for our node. The data inside of it, I could use getters and setters. Normally you'd create getters and setters, but I think what I'm actually going to do is just leave this node class to be part of the tree package itself, just because it's a bit easier and a bit nicer. So maybe if I can take away the public from the class node, what it's going to do is this node class is only going to be visible within the tree package, just because with no identifier or no scope like public or private or something before the class, it defaults to package level. So since it's package level, that means that only anything inside this tree package will be able to see this class node. So back to the binary tree, I should be able to say node and say, I could call it node, and there we go. So it resolves to tree.node, which is perfect. That's exactly the node that we want to be working with. So, okay, fair enough. We have a node, but usually properties of binary trees, since it's a tree, the most important node that we're worried about or that we want to consider is the root. So each tree has a root, and then you sort of traverse the tree from the root. So that's sort of what we're going to start with. We're going to start with a root node. All right, so the next thing that should be of interest is that we want to be able to add nodes to this particular binary tree. So let's create our add method. I don't believe it should return anything, so we'll make it a void, and we'll say, we'll just call it add, nothing fancy. And since what it is that we want to add, you'd think that maybe we want to add a node, but we actually don't want to add a node. We want to actually add the data that will go inside of a node that we're going to be creating. So I'm just going to pass in int data. So since our node object expects int as the data, that's what we'll be passing in. And then we can go about creating our add functionality. So what needs to happen? The first thing I can think of is that we actually need to create a new node, and that node needs to have the data inside of it. So what I'm going to do is I'm just going to modify the constructor for the node. So I'm going to go into the node, and I'm going to create a constructor. I'll create the basic constructor. So I'll do how can I do this? Node. I thought there was a shortcut I can use, but I'll just type it out. It's really not that much text to type out to create a constructor. So this is the basic, empty constructor. I'm not going to have anything there. But the one I want to create is the one where we pass in, we pass in data. And then what that will do is I'll make it set the data for this particular node. So this node that we're talking about right here, any one that we instantiate, I can use this constructor to instantiate this node object to automatically populate the data inside of this, particular instantiated node based on the data that is actually passed in through the constructor. So how that's going to look is I'm going to say node, and then I'm going to say data. So this is going to create a new node, and it's going to automatically populate the data inside of this new node that we're creating because we've added that constructor that takes the one argument. So there we go. We've created a node, but now we need to add it to the tree itself. So here's where it gets a bit tricky. First, we could say, well, if the root is equal to null, then there's no elements in the tree, so then we just need to say, well, then the root is now the node that we're adding. So that we know we always start with at least one element in the tree, okay? So now from there, then we need to decide how it is that we want this binary tree to actually react when you add a new node. One way that I do it is I would create a binary search tree, and what it does is as you add nodes into it, it will decide the best place for the new node to go based on a certain algorithm. So basically what I'm going to say is if the data is less than the node that we're looking at, then we will traverse the left child. Else we'll traverse the right child until we get to a node that we can't traverse, right? So essentially we'll keep on going down the tree until we hit one that doesn't have the appropriate child that we would expect it to have. And then once we hit that point where we can't traverse anymore, that's where we insert our new node. Okay, does that make sense? That's going to more or less be the algorithm, although I'm probably going to be changing this as I'm going, because again, I didn't do much prep work. I'm just sort of going in and creating this video as though or this program as though I was, a student just kind of playing around with it. So let's see how it pans out, and we'll go from there. So let's see. We can assume at this point that our node, our root, is not null. So what we can say is if root.data is, or rather, let's say our data, if our data is less than the root.data, then we should potentially insert this new node along the left child of the root, right? Although at this point, let me think. Do I want to pass in root explicitly? Well, perhaps. For now, I think we could give that a shot and see how it works. Normally, I like to say this. I like to say node, and I would call it node, but I've already done that. I would say traversing node or something like that equals root. And that way, we're always sort of referring to the traversing node every time we're going through this kind of thing. Let me leave it at that for now and see how that goes. So basically, if our data is less than the traversing node's data, then we will need to traverse the traversing node's left child. Okay, and this traverse doesn't exist yet, but this is going to be a recursive method, a recursive call. So I'm going to I'll just create private node traverse, and I will have it accept a node to traverse. So from here, when we want to traverse the node, we essentially need to go down into that particular node's children, right? So let's take a look at that. So we want to go into the node, so that the child node, but we also need to potentially obviously add this new node that we've got. So that's probably something we need to pass in as well. So not only do we need the node, we need to know the node to add. Okay, and that might make this. That's probably a deceiving name then. Traverse. You probably want to say traverse and add node. That's probably a better way to name that particular method. So fair enough. Let's go with that, and we'll pass in our node to add. And I'm going to do an Alt-Shift-R, and that's going to allow me to refactor the name of this. So I can say I did Alt-Shift-R. And again, if you're using Eclipse or Spring Source Tool Suite like I am as an IDE, then you can use that shortcut key. In other IDEs, it's a different shortcut key, but it's just a refactoring tool. I'm refactoring and renaming. So I'm going to rename it to say node to add, and you see it changes all the node to adds or all the previous nodes to now say node to add. And I'm just doing this to be explicit with my variable naming techniques. Okay, so I want to traverse and add this node. So what does this method need to do? Well, we have this node that we've been passed in, which is the left child, and we know that it's that case because we've passed in the left child based on the fact that the data is less than the traversing node's data. Therefore, this particular element that we're adding should be inserted to the left-hand side. But what I'm thinking is the following. I'm thinking maybe we should move this code into the traverse and add node method. I'm thinking that's what we need to do, and we will pass in, or we'll make a call to traverse and add node, and we'll start at the root, and we'll give it the node to add, because I want this to be, like I said, recursive, but it needs to figure out what it's doing all within itself, right? It needs to be contained within itself. So there's all the stuff that we need to figure out is all going to be inside of this method. So now we've got a few things to rename. We don't have data anymore, so now we need to say, okay, where is that data? It's actually inside of node to add .data, and the traversing node is no longer called traversing node. Now I called it node, so fair enough. That's less typing, so I'll use that. Okay, cool. So if the node to add, the data that we want to add is less than the current node, then we need to traverse and add that node based on the left child. Else if the node to add .data is greater than the node's data, then we need to do the same thing. We need to traverse and add node based on the right child, right? But there's a few things that we need to figure out here, because before I probably want to start traversing, I need to check and see if there is a node, the left child of the node or whatever, right? So, because think about it, what if we've decided, okay, we're looking at the current node, and the data is less than the current node's data, so we know we need to add it to the left, but what happens if the the node that we're looking at doesn't have a left child. What happens if this left child doesn't exist? Well, that's the whole point of this method. We want to add our node then as a child of the one that we've realized doesn't have a child, right? So we need to do a quick check. We need to say if the node's left child is equal to null, then that means we want to add it in, right? We want to add in our node to add. How do we do that? Well, we just say node.leftChild equals the node to add. Boom. And then we can keep going further and say else traverse and add node, because that makes sense in that case. Since the left child is not null in this case, then we can traverse it. So we need to sort of do the exact same thing for down here, right? We need to say if the node's right child is equal to null, then we want to add this new node to add into it, right? Does that make sense? Because we need to be able to, since the data is greater than the node that we want to add, the data is greater than the current nodes. And if the current node's right child doesn't exist, then there we go. That's where we want to add our node. That makes sense. And the only other change I'd make is now it doesn't really matter for the return value. I don't really need a return value, so I'm just going to say void. All right. So there we go. I think I've got a little algorithm there that might work for adding nodes, but now we need to test it. So how do we do that? Well, that is all about creating a test case, right? So this is what I was talking about with respect to not using a main method. I'm going to create a new class and call it binary tree test. And this is going to be my test class. So here I'm going to have an annotation called @test, and I'm just going to create a public void test class, and I'm going to import my my annotation based on the JUnit test cases. Now it doesn't seem to be liking that. It says test cannot be resolved to a type. Let me go back to my linked list test class. This one is going along just fine. That's an import from org JUnit. So let me go into this one and try importing it. Maybe it's confused. Yeah, it looks like it was just confused. That was an odd little, unexpected behavior. I've never seen it do that before. But all it is it's an import from JUnit. And what this allows us to do is run this method, run this test method, without having any sort of static functionality involved to it, or involved with it, like we would have otherwise with the public static void main method. So I want to test this binary tree now. So I want to create a new binary tree. I'll call it tree equals new binary tree. And then I want to say tree.add, and I want to add a node. So I'll say 50. Does that sound good? So the 50, there's nothing in this tree right now, so 50 should immediately be assigned as the root element, right? And then I'll add another element. I'll say 25. So now that should be added as the left child of the root, right? And then I want to say add, let's see, let's try 75. So that'll be added as a right child. And then let's try 10. And then let's try, let's see, 30. And then, boom, 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 boom. Let's try, well, that's good enough. Let's just see how that works. First of all, I want to run my code and just see if there's any catastrophic failures. That would be my first sort of test. So I'm going to right click. I'm going to go down to run as. I'm going to say JUnit test. It'll run, JUnit results. I'm going to pull up over here. And you see that the test passed. All right, fantastic. There's no big catastrophic failure, so that's great. But now I'm interested to see what the results are, right? So I'm going to put a breakpoint right here on the last tree.add, and I'm going to run this again. I'm going to say debug as instead of run as JUnit test, and it will hopefully hit the breakpoint, and it's going to switch views here, and now we've hit a breakpoint where we're going to add the 30 data element. But first I want to look at what the tree looks like, right? I should have a tree that has 50 as a root, 25 to the left, 75 to the right, and then 10 will be a child of 25. All right, so that's hopefully what I'll see. So let me hover over tree and see exactly what it is that we have to work with here. So we have the root, which is 50, fantastic. The left child is 25. Great, that's what we expected. The right child is 75. Great, that's what we expected. And hopefully 25 has a left child of 10, which it does. Perfect. So far so good. And then let me run the add 30, and then hopefully that, let me look back and see if that was added correctly. So our, you see that it's in red here to say, oh, we have a right child that just got added to 25. So hopefully that will be the 30 element. Perfect. So that's great. So far so good. I can't see any issue with that. So let's put it through a little bit more of a ringer and start adding more elements to it. All right, so let's do, let's just overload it in the sense of a whole bunch of elements. Let's do 60, 65, 80, 85, let's see, 100. Okay, so let's see what that looks like now at the end. Rerun this. We'll do debug as JUnit test. We've gotten down to the bottom, so let's see what our tree looks like now. Root node of 50, 25, 75. That makes sense. Left of 25 is 10. Left of 10 is 1. Great. So that makes sense. So now we are dealing with 25. Right of 25 is 30, and then that's it. Okie dokie. Then we have our node here, which is 75. Left of 75 is 60. That makes sense. Let's see. Right of 75 is 80. Okay. Right of 60 is 65, which makes sense. And let's see. Right of 80 is 85. Very good. So then we do the 100 is the last one, and you know I can only assume that'll be correct. So that should be all the way to the right. So if we go right, 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 we see 100. So that makes perfect sense. It looks like our tree is building itself out nicely. So I can say that the add function so far, so good. It seems to be working. So let me go back to my original view here, and we can say that our add method is working. So now what else do we want to do? Well, we want to be able to delete nodes from the tree as well, right? So this is a tricky one. Before, actually, I want to do delete, I want to do traverse, because like I said, delete is tricky. So let me do traverse. So let me say public, let me say void, and let me say traverse. Okay, and we will traverse, obviously based on our root element, which already exists in the tree. So we don't need to pass anything in, because we want to traverse based on the root. Now, there's a bunch of ways to do a traverse. Like I said, there's an in-order traversal, there's a pre-order traversal, and a post-order traversal. I don't want to create 3 different methods for it, because it's actually fairly easy to just modify one method to show you the difference between all of them. So I'll show you that now. Just call it traverse, and we'll, sorry, that's my phone going off. I should have put on silent. We'll go through traverse step by step. So how do we traverse? Well, the first thing we want to do is we want to make sure that the root is not equal to null, right? Because if the root is equal to null, then there's nothing to traverse, and we do nothing. So there you go. Problem solved. If it is not null, then we want to traverse through the root, right? So we want to decide what kind of traversal we want to have here. So I'm going to be talking about the one in the middle. There is pre-order traversal. Then there is in-order traversal. Then there is post-order traversal. Okay, so these are kind of in order here. Pre, in order, and post. So we're going to be talking about this one right now, in order traversal. So what does that look like? We will have to go through the root to do this in order traversal. And we're just going to keep on going down the left side of the tree until we hit the sort of the last element along the left-hand side, and then we're going to sort of output its value and go forward from there. So we'll say this. We'll assign node to traverse equal to the root. So we start there. And we say if node to traverse has a left child, okay, it's not equal to null, then we call traverse based on the left child. Now, let's see. We can, since I'm calling this traverse, what I will probably do, well, maybe this is what can we do here? I want to call traverse again, but I need to pass in the left child because we want to traverse that left child. But since I've done this, I don't have anything here that I can put in. I don't want to have to put in a node, right? I'd have to put in node to traverse through, but then that sort of breaks what I said initially, where we don't have to put a node in there. So what can I do? Maybe what I can do is I can copy this, paste it, create a private method, and have one pass in the node. There we go. So that's sort of a hack that you can do. And then in this case, what I'll do is since I've already done the check for the root, I won't have the check for the root anymore. And did I do that correctly? There we go. And now we're passing in the node to traverse. So we don't need to worry about the node to traverse because I think we're already looking at the node we may or may not want to traverse, although I might change my mind in a second. So then this is where we can do all of our handiwork. So I guess I can call this in order traversal after all. You know, maybe this is just how it's going to work out. So we can do in order traversal. So fair enough. We want to then do the exact same check. We want to say if the node's left child is not equal null, then we want to do, the in order traversal with this node's left child. Okay, so we want to keep on doing that over and over and over again until we hit the point where the left child is no longer null, right? So, where the left child is null, because this whole time it is not null. We want to hit it where it is null. So once that left child is null, we want to output what the node has in its data, right? So we want to say system out, and I will say node.data. Okay, so we're going to be doing a recursive call over and over and over again until we hit the far left node that doesn't have any more left nodes, and then we're going to print out its data. Okay, and then what's going to happen is this method is going to, since it's a recursive method, it's then going to start backing itself up and then perform the next step. And the next step is to check and see if the node has a right child. Okay, so if the right child is not equal to null, then we do an in-order traversal, and we traverse with the right child. All right, and I think that's it. I think that's all we need to do for the in-order traversal. If my university knowledge that was so many years ago comes back to me, and I think that's correct. I think that's all we need to do. And so now the only special case here is that we have this traverse where we check to make sure the root is not equal to null, but we haven't handled the case where what happens if the root doesn't have any children, right? So we can say else here. So if the root doesn't have any left children, then we can say do a sys out with the node to traverse and just output its data. So then all we're going to be doing is just outputting the root's data. Okay, so fair enough. Let's have that. Let's leave that alone. Let's go to our test case, and let's call a traverse on our tree, and let's see what happens. Okay. Hopefully it'll all work out, but you never know. I just did this. So okay. So here we see the output is 1, 10, 25, 30, and then it stops. So that is not good enough because we want to see all these numbers that were added into the tree. So clearly there's an issue with my algorithm. So let me just go in and take a look and see if I can figure out what the problem actually is. The only thing I can think of is that I would need to also put a system out over here after the right child. I'm not sure if that's true or not. Let me rerun the test. No, see, that's causing duplicates down here, so that's not right. All right, so I guess what we can do is just start debugging, right? We'll just go through it and see exactly where the bug is and go from there. So I'll rerun this test, only now I'm going to rerun it as in debug mode. And we'll jump in. So now at this point, we should have an actual root element that has an entire tree built up around it, right? It should be all the way to the root 100 is what we should have, so we do. So this tree is nicely created. So now let's go through and see what our problem is in the traversal. So we're going to check and see if we have a left child, which we do. So I'm going to call in-order traversal with the left child. So now we should be looking at, okay, data node 25. So then we say, okay, does node 25 have a left child? Yes, it does. So we do in-order traversal. So now we're looking at node 10. So now does node 10 have a left child? Yes, it does. So we traverse. That's node 1. So now node 1 does not have a left child. So we output node 1 into our console. Fantastic. Now we check and see if node 1 has a right child, okay? Which it does not. So we pop back on our stack up the stack until we get to the next level up. So the next level up, the node is 10. So then we output that node, and we check and see if 10 has a right child, which in this case it does not. So then we pop up the stack again, and now we're looking at node 25, right? All right, fair enough. So now we output node 25. Does node 25 have a right child? Yes, it does. It has 30. So we go and we traverse with the right child. Then with the right child, which is in this case 30, we check and see if it has a left child. It does not. We output the value, fair enough. Check and see if it has a right child. It does not, fair enough. Then we pop up the stack, and this is where it pops up the stack. So here's our problem. We've hit our root node, and now we need to do an in-order traversal from the root node, which we are not doing. So that's the problem. Fair enough, we can fix that. So we can say else if node to traverse, because now we're looking at the root again, has a right child. So if the right child is not equal to null, then we do an in-order traversal with the right child. Okay, so let's see how that pans out. Let's go back to our test. I will just run it as is. And it seems like it didn't make any difference whatsoever. Did I make a mistake over there? Oh, probably, yes. I did an else if. I should not have done an else if. My apologies. If you notice down here, these are both if and if, not if and else if. So that was my mistake. So then what we can do here is we need to tweak our code because this system.out will cause problems. So what we should do is we should do an if check right away. We should say if node to traverse dot left child equals null, then we do the system dot out, and then we can say else and wrap both of these in the else statement. Okay, so you see what I've done there? I'm saying, first of all, check and make sure the root is not null. If it's not null, then we assign it to traverse. But here's the, the special case. If the root has no left child, and I should probably say the root or the node to traverse also has no right child. Okay, so this means that the root has absolutely no children whatsoever. If it has no children, then we just output the root itself, and that's it. Okay, fair enough, done. Let's continue. But if it has either a left child or a right child, then it's going to go in here and hopefully output everything in the correct order. So let's go back again and run our code and see what we get. There we go. So now we go 1, 10, 25, 30, 60, 65, 75, 80, 85, 100. So you see all of this is in order where 1 is the least and 100 is the greatest. And that is exactly what we want to have happen. So that's perfect. That is the in order traversal that we've just created. All right. So now let's go back to our binary tree and let's change this so that we want to do something else. So let's try let's change it to be the pre-order traversal. Okay. So let's see. How can we do this? Let's just change the name of this. Let's say I'm going to do my Alt Shift R again to change all the names all at once. I'm going to call it pre-order traversal. And the only thing I'm going to do differently is I'm going to take this system out print line and I'm going to move it up to be before the check for the left child. Okay, that's it. That's all I'm going to do. I'm going to move the system.out up. So that's going to turn it into a pre-order traversal. So if I rerun my test, boom, you see that now this is a pre-order traversal of the actual tree. Now I'm noticing there is one issue. I don't see the actual root element, and see it's coming in to the point where I should have put the roots output in this piece of code here, but I'm really just recreating this pre-order traversal thing. So what is it that I need to do here? I think all I need to do is just call pre-order traversal, which is what I'm doing with the left child. I just feel like I have a redundancy here. So really what we should have is there should be a system out where I output the node to traverses data, right? Because that's exactly what I have here. It's the exact same thing that I'm just recreating right here. So what I should be doing here is I should be calling pre-order traversal not with the children. I should be calling pre-order traversal with the node to traverse. I believe that will simplify things, if I'm not mistaken. Who knows? Let me rerun this. There we go. So that makes sense. Now we have 50 that shows up first, which it should, and then 25, 10, 1. So if you think about it, this is going along the left-hand side of our tree and outputting the results immediately. So 50 is the root, and then the left child is 25, and the left child is 10, then the left child is 1, and then we go up, and we hit 30, et cetera, et cetera, et cetera. So this is exactly how you would have a pre-order traversal, and this is useful for things like if you would need to recreate this tree in some way, shape, or form. You would need to, let's say if you wanted to serialize this tree and store it somewhere, you would use a pre-order traversal, and that way you can sort of keep track of how these nodes should be added. But please note, if you're doing that kind of thing, you would also want to keep track of the nulls as well. And that's very important when you're doing a serialization of the entire tree. You'd want to also output the nulls. So 50, for example, it would be 50, 25, 10, which would be fine. And then it would be 1, and then it would be null, null, because 1 doesn't have any children. So you'd want to output the fact that it doesn't have any children. Okay? So there you go. And then hopefully you figured out in this case, let me go back to the in order traversal. So I'll move the system out print line back to the in order traversal position. I'll change the name of this to be in order traversal. And I'll run this again, and now you can see that's back to being in order, but it must have missed the root element last time. It probably did not display 50, so I just missed that because there's a whole bunch of numbers. So now you see it displays the 50 appropriately: 1, 10, 25, 30, 50, 60, 65, etc. Okay, so fair enough. You know how to do pre-order, you know how to do in order, so can you guess how to do post-order? Hopefully it should be fairly straightforward for you. You just move the system out down to go below the right child, and that's it. So now we can change the name to be post order, and we can rerun, and there we go. So that's what the post order traversal would look like for the tree. I didn't do any homework to see what uses the post order traversal would give you. I don't exactly know, but I just know that there is a post order traversal algorithm, and this is what it is, and this is what the output would look like for our tree that we've constructed. All right, cool. So now then there's the next topic that I would probably want to discuss is the deletion algorithm. Now the deletion algorithm is going to be very tricky, as I said, because imagine, let's I wonder if I can show the actual tree somehow. I guess there's no way for me to show the tree nicely in this view, but if you could think of the tree itself, where you have 50 as the root, what would happen to the tree if we decided to delete the very root element? Okay, what should happen to the whole tree? The whole tree is going to be affected by that because the root is gone. So now we need to shuffle everything around in such a way that we'll have a new root, and then there's a whole bunch of stuff that goes along with that. That's actually a fairly complex algorithm, and I think I'm going to have to do a bit of research before I actually try to just jump into it blindly, because I would probably take up a whole bunch of time going through this deletion algorithm. So let me do a bit of research, and then I can go and show you exactly how you would recreate the deletion algorithm. All right, sound good? Sound good. All right, so in a blink of an eye, we are back. I just did a whole bunch of research, and it turns out that yes, this is indeed a complex process for deleting a node. Now, what I've done here is I've created a delete method inside of my binary tree, and I've outlined 3 cases. So these are the cases that we need to worry ourselves with. Case 1, so this is like easy, medium, and hard. Okay, so it's in increasing level of difficulty. Case 1 is where the node that you want to delete has absolutely no children. Okay, so that's an easy case, because if the node has no children, then you just delete it from the tree structure, and we're done. If the node has 1 child, it's a little bit more difficult, but still pretty straightforward. We will essentially get rid of that node by assigning its parent to point to the node that we want to delete's child. Okay, since it only has 1 child, we just point the parent to be the parent of this node to be the point down to be the child of this node. So I'll explain that when I get to it a little bit better. The case number 3, where it has 2 children, is very tricky. But once you've properly implemented case 2, it becomes a little bit less tricky. In case 3, you actually need to find the successor, so the next node that comes from this one, the one that we want to delete, and then we traverse down all the way to the left from that next node to find the actual next node, and that's the one that we sort of copy up into this node, and then perform. Anyway, so there's a whole bunch of steps that go along with case 3, but I'll explain those when I get there. So the first thing that you'll see also that's different is I implemented a find algorithm. So this is going to be important because when we want to delete a node, you can see that we're just saying delete, and we pull in a value, or we give it a value that says this is the node that we want to delete. In order to delete that node, we first need to find it in the tree to either verify that yes, it exists so we can delete it, or no, it doesn't, so we can't delete it. And if we have found it, then we need to use that node and have the actual node object to modify and whatnot for the actual deletion. So I've implemented a find algorithm. So I'll just quickly walk you through it. So you see it's just find, and you find by the value. So just like if you were going to delete, you're saying, I want to delete this, so therefore I need to find it first, pass in that same value. If the root is not equal to null, obviously if the root was equal to null, then there's nothing to delete, so therefore we return null. If there is something to delete, that means that there is at least a root element. So if there's at least a root element, then I say return find node. So I've declared a sort of a private method here, where I pass in sort of the beginning. So I say the root is where we start our search, and I'm passing in I'm instantiating a new node based on the value that we've passed in of the node that we want to find. So we're creating a new node, and that's just kind of what we're doing to, in order to use our searching and whatnot, and also passing stuff in. So in any case, you'll see what we do here. So we say find node, pass in the root element. First of all, we say if the search is equal to null, then we return null, because there's nothing that we can do at this point. If our search hits a null element, or if our search becomes a null element, then there's nothing more we can do, so we return null. If the search data is equal to the node's data, so if the node's data is the data that we're actually searching for, so that's what we're interested in finding. And the search data, this is the actual one where we're iterating through and flipping through each node through the tree, and that's what we're sort of replacing as we're going along. If those two are equal to each other, then boom, we found our node. That's the node we wanted to find. Here it is. So we just return search.data. Notice that we return search.data and not node.data. That's important to note, because search.data will actually have the full structure of the node. Okay, left child, right child, etc. Because if you notice, the node that we created was just a new node with a value in it, so we didn't assign any left or right child or anything to it. So it's important that we don't return that, because that would give us bad data. So we want to return the actual node that exists already in the tree. Make sense? Otherwise, here's where we get sort of fancy with our searching algorithm. We want this to be a nice recursive algorithm. So this is how I did it. I create a new node, which I call the return node, and I say find node. So this is a recursive call back to itself, where this time we are searching on the left child of the current search node. So you see how if we start with root, okay, if root is what we start with, then search is equal to root. Therefore, search is not equal to null. Let's assume that the data that we are searching for is not at the root. So then this part of the algorithm will still remain false. And we'll go into this part of the algorithm, which is sort of the meat of the algorithm. So search right now is the root. So we'll say find node based on the root's left child. All right. So if the root doesn't have a left child, then it's just going to go in and it'll say search equals null, return null, and it'll bounce back and go to the next line of code. If the search does have a left child, it will bypass this. It will actually check to see if that data does indeed match. If it doesn't match, well, then it tries to search through that left node. Okay, and it just keeps going down the left chain until we either find the data or we don't find the data. Okay, and eventually it will bounce back, okay, and it'll say if return node equals null. So this is important because if we actually have found our node, if at some point we found our node with our left child search, it will return search, right? So if at some point we found our node through the left children's search, we will have found our node in our tree, and we will be returning that node. But remember, this is a recursive algorithm, so it's going to come back to this point and hit this if statement. If we didn't do this check, if we didn't say if return node equals null, it would overwrite our findings with the search through the right child. Okay, because if let's say we found our node on one of the left children, what's going to happen is it's going to go through the right children, and it's just going to keep on returning null, 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 and that is essentially what will have been returned if we didn't do this check, right? Because we say return node equals find node. So this would have returned null in the case that we found our child along the left side of the tree. This will return null, thus assigning it to return node, and thus returning null, and we are not happy. So we need to make sure that we say if we haven't already found return node by checking to see if it's null, then and only then, if we haven't found it, we search through it through the right children and assign it. All right? Cool. So there we go. I didn't want to have to go through and actually, code that up with you. It's easier to just have it there and explain it. So now, having said that, we have our find algorithm. So now we can work on our delete algorithm. So as you can guess, the first thing we need to do when we try to delete something is that we want to first find that node. So we can say node to be deleted equals, and we can say find based on val, right? The value that we pass in. So we're finding a node based on the value, which we'll call this, which we'll call our recursive algorithm, and hopefully return the node that we found. Otherwise, it will return null. Okay. So if we say if node to be deleted equals, or I should say not equal to null, that means that we actually found something. If we found something, then we can delete it. If we didn't find anything, then there you go. It just hits return false, which means it flags the person who called delete to say, oh, we weren't able to delete this node. So sorry, cry me a river type of thing. So fair enough. Now we've hit our part at the part where we want to delete the node and we found it. So what do we do? Well, obviously we need to delete it. So let's start with case number 1. So we obviously need to check and see if this node to be deleted has any children, or rather has exactly 0 children. So we can do that by saying if node to be deleted left child equals null, and node to be deleted right child equals null. So like I said, this is case number 1. This is the easiest case. If these two are both equal to null, then we could just delete the node. But how do we delete the node? Okay, this is a critical part, and this is where I realized I had gone wrong when I had created the add algorithm above. I think it's above anyway. Traverse and add node. I made a boo-boo. When we are deleting, we need a reference to the parent node. Okay, so not only do we need a reference to left child and right child, but we also need a reference to parent. Because think about it, how can we delete a node from a tree without a reference to its parent? That's going to be tricky. So what we'll have to do is for the node to be deleted, essentially what I want to say is I want to check if the node to be deleted is the left or right child of the parent of the node. Okay, so in other words, we're checking to see if the node to be deleted, we'll check its parent. So essentially we'll go up. Let's say, we're trying to delete node number 1 with value 1, and above it we have a parent of value 5 or something like that. So we would go above it and check the parent of node 1. So we go to node 5 and we say, is node 1 a left or right child of node 5? Okay, and in a case of the binary search tree, we know that it's going to be a left child, although we'll do the check, and we'll see, okay, it's the left child. So now node 5 has a left child of 1, and we want to delete node number 1. So how do we do it? All we do is we say node 5.leftChild is equal to null. We just get rid of that left child. And then there you go, the tree is good to go. We've deleted that leaf, if you will. So we need a reference to the parent. So let me go back to my node and definition itself, and I'm going to add another property. I'm going to have a parent. Okay, so since we've added it in here, we need to actually make it function. We need to populate it. So how do we do that? It's actually fairly easy. It's going to be populated when we add a node. Okay, so when we add a node, we call traverse and add, and then inside of here, where does the actual adding happen? I believe it's right here. So node.leftChild equals node to add. So this is where we actually add a node into our tree. Okay, so before we actually make this left child equal something, we can say node to add dot parent is equal to node. All right, so you see what I've done there? Node to add, the node that we want to insert into the tree at this point. Remember, we switched from deleting to be adding, so think about your adding mindset. We want to add this node to the tree. This node right now that we want to add only has, if we go backwards, here we go, this node to add, all we've done is create a new node with just the data inside of it. So there's no reference to a parent. So we need to add that reference. So we say node to add dot parent equals node. And we note that that's true because we're about to add the left child of that node. So this node's left child is going to be the node that we want to add. So since this node's left child that we're now creating is going to be the node that we want to add, it's completely safe to say that we want to set the parent of this node to add to be this particular node, because that obviously is going to be the parent. All right. And then we can do the exact same thing down here. We can say node to add dot parent equals node. And there we go. We are now properly keeping track of all the parents for all of these nodes. All right, cool. So now we can go back down to our deletion algorithm. So we can say, all right, now that we know that we have a reference, a proper reference to the parents or the parent nodes, we can start with our checks. We can say if the node to be deleted, so we can say get the parent. All right, so we're saying the node to be deleted, check the parent, and check the left child. If the left child is equal to the node to be deleted, then we have information about what it is that we need to do. Else if the node to be deleted's parent's right child is equal to the node to be deleted, then we know that we need to do something else. So in the case that the node to be deleted's parent's left child okay, is equal to the node to be deleted. So this was the case I was talking about with the node 1 and node 5. So maybe I can draw a very quick diagram. I'm not sure if this will be helpful or not. Let's see, let me try up here. So we'll say the node is equal to 5. And then let's do our right left. And let's say we have 1. And let's say this one also has, I don't know, 10 or something like that. And then 10, I don't know, maybe 10 has 11. It doesn't really matter, whatever. So let's say this is our tree structure. And what we're saying is we want to delete 1. So we want to delete this one. Okay, we want to delete node 1. How do we do it? Well, like I said, node to be deleted, which is number 1. We check the parent, which is 5. And we check the left child of 5, What is the left child of 5? The left child of 5 is 1. So what we're saying is the left child of 5 equal to the node to be deleted? Is 1 equal to 1? In this case, yes it is. So now we've identified the node that we want to delete. Okay, you see how that works? And then how do we do it? Well, we just say node to be deleted dot parent dot left child equals null. So what we're saying is node to be deleted dot parent, okay, the parent, which is 5, the left child is now equal to null. So what we're doing is we're doing this. Boom, gone. Okay, so there we go. We've successfully deleted that node. Or we have the vice versa situation where, let's say it is this situation. Okay. So what we want to do here is you want to say if the node to be deleted's parent's right child is equal to the node to be deleted. So we're saying we want to delete 10. So we check the parent and check the right child. The parent's right child is 10. Is that equal to 10? Yes, it is. So therefore, we want to say, boom, node to be deleted's parent's right child is equal to null. And there you go. That is case number 1, and that is how you delete a node with case number 1. Now, here's where I want to get a little bit tricky. I want to take all of this, and I want to pull it out. And I want to assign it to another method. I'm going to assign it to a private method called delete case 1. Okay, and I'm going to paste it in here. So I'm going to pass in node to be deleted. There we go. Okay, and I'm just going to say delete case 1. Delete case 1, and I'm going to pass in node to be deleted. Okay, and I'm going to be doing this because, well, actually, for this one, it doesn't really matter. It's for case 2 and 3. I want to be able to call case 2 from case 3, but we'll get into that. So we have successfully implemented case 1. So now what's case 2? Well, case 2 is node has 1 child. So how do we do that? Well, we can just say if, since we've already checked here, we've already checked to see if the left child and the right child are null. So we know that that is not going to be the case. It's not going to be the case where both children are null. So we know it's safe to say else if node to be deleted dot left child is not equal to null, then we know we have 1 child and it's the left child. Okay, and we can do the same thing else if right child. See what we're doing here? So these are both going to be case 2. All right, so this is case 2 where left child should be deleted, and this is case 2 where the right child needs to be deleted. All right, so because the left child not equal to null, therefore it should be deleted. Right child not equal to null, though, therefore that's the one that should be deleted. So then what are we going to do? Well, we can call delete case 2 and pass in node to be deleted, and same thing down here. So what I'm going to do here is I'm just going to hover over it, and I'm going to say create the method. So it's going to quickly create a private method for me, less typing for me and less time for you guys to watch. So let's figure out case 2. So case 2 is a little bit more difficult, but not exactly. So let's take a look at what it is that we have here. So how could I do this one? Let's say we have 50, and I'm not going to draw the lines anymore because those just take up more space than they need to. So I'm just going to do this for the tree. And what else do we have? 10, let's say. And for the sake of argument, let's put 65 and, I don't know, 80 or something like that. Okay? So does that make sense, this tree structure we have here? So let's say the node that we want to delete. Ooh, let's see if we can do it. Is that how we had it before? No, we had it like this. Okay, let's say we want to delete 25. So you see how this is equivalent to case number 2? This 25 node that we want to delete has exactly 1 child. In this case, it's a left child. So that meets our case 2 criteria, which is node has 1 child, exactly 1 child. So 25 has 1 child, which just happens to be the left child. So how can we delete that? Well, think about it. All we need to do is take 25 out of the equation. So that means that 50 should no longer point to 25 from its left child. 50 should point to 10 as its left child. That's all we need to do. So just take the pointer down from 50's left child and make it equal to 10. All right? Piece of cake. That'll get rid of the 25 completely. So how do we do that? Let's see. We need to say first we need to figure out if it's a left child or a right child situation that we're dealing with, okay? So we need to say if the node to be deleted's parent's left child is equal to node to be deleted. All right, you've seen this code before. Else if node to be deleted parent right child is equal to node to be deleted. Okay, you saw that up here or down here already. Then what do we need to do? Oh, sorry, double equals, not single equals. So if the left child, the parent's left child is the node to be deleted, then what do we need to do? Well, we need to say node to be deleted's parent's left, not equals, left child is now equal to what? Well, I said I want it to be equal to 10. How do we get to 10? Well, we just do node to be deleted dot left child. But here's where it may get a little bit tricky. We're not sure if the node that is to be deleted, if it has a right or a left child, right? We would know up here which scenario we hit, but down here we don't. So it's kind of a duplicate sort of code that I'm doing in here. There's probably an easier way to do it, but because we want to have case 2, delete case 2 be an actual method because we want to be able to call it again, I'm going to do it this way. There's probably an easier way, but this is what I'm landing on. So we need to do this check again. We need to say if the node to be deleted left child is not equal to null. So if the node to be deleted has a left child, which is this case, 25 is the node we want to delete, it has a left child, then we do this, okay? We assign the parent's left child to be equal to the node to be deleted's left child. Otherwise, we could say else if node to be deleted right child is not equal to null, then we can say the node to be deleted's parent's left child should now be the node to be deleted's right child. So the situation I'm talking about here is if we have, 25, what would this be, 30? Like so. I guess we can sort of do it like this. I guess that's just, there we go. Fair enough. So the node here has a right child. So then that would be the one that we want to assign. So then we would say node to be deleted's parent's left child. So node to be deleted's parent's left child is now equal to the node to be deleted's current right child. So that would be this one. So we would say 50 now points to 30. Boom, like so. And 30 will just drop out of the equation because there's going to be no more references to it. Sound good? So there we go. That's essentially what we need to do there. Now, all we need to do here is just copy-paste, essentially. But we need to be careful when we copy-paste because this is a little bit tricky. So in this case, the node to be deleted's parent's right child is equal to the node to be deleted. So this is the case where 75 is trying to be deleted, right? So the parent's right child is equivalent to the node to be deleted, which is 75. So now what do we want to do? You want to assign 50 to be, well, I guess this is not a good situation because this one has 2 children, so that's not the one we're looking for. So let me just do this. Fair enough. So what would we do? We need to say if the node to be deleted's left child is not equal to null, then the node to be deleted's parent's right child, remember we are interested with the parent's right child, is equal to the node to be deleted's left child, which makes sense because we know the left child is not equal to null. And here we say right child. So the node to be deleted's parent's right child is now equal to the node to be deleted's right child because we know it's not null. Whew. So there we go. That's case 2. And believe it or not, that's not the most complicated one. The more complicated one is case 3. Delete case 3. Node to be deleted. Boom. So let's go back up to our regular old delete method. So what is case 3? Case 3, we can just say else. All right, because we know that we're not in a situation where both children are null. We know we're not in a situation where the left or right child singularly is null. So therefore, the else means that this is where we have both, node has both children populated. Okay, so we obviously need to call delete case 3, pass in node to be deleted. Okay, so how is it that we have to go about doing this? Well, this one is, like I said, quite tricky, and it's going to involve a little bit more fancy work with respect to algorithms. So let me try and set up the scenario that we are interested in. Let's say we have 75, and we have oh, I don't know, 60 and 80 and let me think. 80 has I don't know, 76, let's say. Try to space these out a bit so it makes sense. And I don't know, 90. So let's say the case is that we want to delete 75. What is going to happen? Well, believe it or not, the algorithm is you take the node where you want to delete. We know that it has two children. It has 60 and 80. Okay? What we want to do is we want to traverse down to the next element. Okay? So the next element from, or the successor to 75 is 80, in the sense that it's just the right child. And then we need to traverse down all the way to the left. Okay? So in this case, we go down to 76. And then, so that's what we do. If 76 had a child, which wouldn't make sense in this point, we need to turn to 77, and then this would be 76. Then we would say, okay, this is the one we want to delete, so we go down to the right once, and then we go all the way to the left. So in this case, it would be 76, again, that we want to do something with. So what is it that we want to do something with? What's the formula? Well, we copy 76 into memory. Okay, so let's assume that we've copied this into memory somewhere. We delete it from the tree by removing 77's pointer to it. Okay, we've done that before. That's actually case 1. Okay, case 1 is where we have, or sorry, that's incorrect. This is case 2. Remember, case 2 is where we have exactly one child. So this is why we created a delete case 2 formula up here. Okay, delete case 2 is because we want to be able to delete 76 at some point, which is going to be case 2. So we copy 76 into memory. We invoke delete case number 2 on 76 to delete it from 77. And then we overwrite 75 with 76. All right, so now we've successfully deleted 75, and our tree is still correct. All right, so that's the algorithm. Again, we can backtrack there. We go right once, and then we traverse all the way down to the left. So how do we do that? Well, we're going to have to create an algorithm that returns a node that does a min traversal, essentially. Okay, so it gets the minimum node on one, I say minimum left traversal. How about that? Okay, and we do a min left traversal, and I'm assuming we need to do it based on a node to actually traverse on. So let's assume we're passed in a node. In this case, it's 80. So what can we do? First thing we say is if that node, so if 80 has a left child, if let's say for the sake of argument, it doesn't have a left child. Okay, remember we want to traverse left only. So if 80 didn't have a left child, then what would we do? Well, we would just return that node. Okay, we would just return 80. Make sense? But we're not in that case. We haven't hit that case. So what we want to do is we want to do a min left traversal. We want to do a recursive call on the left child of that node. And I should say we should return that traversal. Okay, so in this case, we're passing in 80, and we're saying traverse. So 80 has a left child, so this gets equates to false. So then we return min left traversal with a left child. So we're passing in 77. Okay, then it goes back up. Does 77 have a left child? Well, in this case, yes, it does. So this is false. So then we traverse with that left child. So we pass in 77's left child, which is 76. And then we say, does 76 have a left child? No, it doesn't. So then we return node. And then it'll return node, blah, blah, blah. There we go. So that's the min left traversal algorithm. So that's one, step down, or one algorithm down. So now what we need to do is remember, we want to delete 75. Okay? So 75 is going to be the node that is to be deleted. So what we want to do is we want to call min left traversal on 75's right child. Okay? And it's always going to be the right child. So we say node to be deleted's right child. All right? And that will return the min node, essentially is what we could call it. All right? So this is going to be min left traversal. We're going to be doing the min left traversal on the right child. So we're taking the node that we want to delete, passing in the right child, and doing a min left traversal on it, which should go all the way down to 76. It should return 76. And then remember what I said I wanted to do. I wanted to copy 76 into our memory somewhere. Okay? We want to store it in memory, which is what I'm doing here with min node. That's our temporary storage for min node. And then what did I say we wanted to do? We wanted to delete 76. How do we do that? Well, we invoke delete case 2. We know it's going to be a delete case 2 because it has a child. Now, is that true? Let me think. Yes, that's got it. I believe that has to be true in all cases. So we're going to invoke delete case 2 on min node. All right. So what that's going to do is it's going to delete 76 from 77. Fair enough. But now what do we need to do? Well, now, like I said, now that we've deleted 76 from our tree, we need to paste it into 75. So how do we do that? Well, that's a little bit more tricky, but we can figure that out. We need to, again, say for 75, its parent, what pointer is pointing to it from the parent. So again, we need to say node to be deleted dot parent dot left child equals node to be deleted, then do something, otherwise do something else. Okay, so this is the left child. So we're saying if well, let's not do this one yet because it's not the one I'm interested in. So we'll say node to be deleted's parent's right child is equal to node to be deleted. This is this situation. So if we look at 75, this node to be deleted, we look at the parent's right child. So the parent's right child is indeed equal to the node to be deleted. So let's do something. What is that something that we want to do? Well, we already have our min node that we want to have replacing 75. So essentially all we need to do is say that the min node itself, we need to get the properties set in the min node equivalent to what 75 has, right? So essentially we want to take 76, which is now in memory, and give it all the properties that 75 has, right? So we want to say, okay, min node dot parent is equal to the node to be deleted's parent. There we go. The min node's, min node's left child is equal to node to be deleted's left child. And the min node's right child is equal to node to be deleted's right child. So there we go. Now we've copied over all the properties. Remember, we don't want to copy over the data property because that wouldn't make sense. We want it to now say 76 instead of 75. So we wouldn't, copy over the data from the node to be deleted because otherwise it's like we're doing nothing except for deleting node 76, which would be bad. So there we go. We've copied the properties, and now we want to replace 75 completely. So how do we do that? Well, we've done that before. We just replace the pointer that the root or the parent has pointing to 75. Okay, so what we can do here is say that the node to be deleted's parents, again, we know it's the right child because we've done this comparison here, is equal to min node. Sound good? Now, I'm going to move this stuff up because otherwise what I'm going to be doing is I want to copy paste and have the exact same thing happen, only this time I'm going to say the parent's left child is equal to the min node. But you see here I'm duplicating this code, so I'm just going to move it up to be before the if statements, and just delete it from the two places. Okay, so there we go. We've assigned the min nodes the correct the correct information, and then we've deleted the appropriate node using our parent's left child or right child pointer here. Phew. So I think that's good enough. I believe that will serve its purpose. So now if we go back to binary search tree test, what I've done is I've changed the traverse to include the null pointers, so that'll help make us understand the tree. So I'm going to run this code, and what this is going to do is just going to show us the traversal of the tree, and you see here that we have 75. So 75 appears, and then it has 60 and 65 and 80, etc. Okay, you see that 75 still exists. Fair enough. Now let's move the traverse down to go after the delete. So we want to delete 75 to see what happens. So now I'm going to go back and rerun this test, and hopefully you'll see that 75 is gone, and indeed it is. But in this case, I'm wondering if we've made an error, because I don't see anything bigger than 75. Did we have? Yeah, we certainly had stuff bigger than 75. So perhaps I've made an error in some of my code, so I need to look into that. So let's just debug and see what it is that we have going on, and see where it is that we went wrong. Okay, I did a bit of debugging there, and realized something. The problem is back up here. So in my actual delete method, where I'm narrowing down case 1, 2, 3, I made a mistake in my if structure here. You may have noticed it before I did. I'm sure you might have been screaming at your computer or something. But here's the problem I just realized. So we're checking to see if both children are null, which is fine. And if they are, then we're assigning it to delete case 1. But here's the mistake. I immediately go into assuming that we're dealing with delete case 2, where that's not the case. Because let's assume that we're in a situation where we're in delete case 3, which is where we have both children. It's going to accidentally and incorrectly assume that in the case that we have both children, one of them is going to be not null. So it's going to incorrectly identify it as a case 2 and treat it like a case 2, which is incorrect. What we need to do is say else if node to be deleted's left child is not equal to null, and the node to be deleted's right child is not equal to null. Then we know that we're in a case 3 situation, so I can take this code and move it up into this else if, and that's the case 3 situation. Now it's safe. Now we know if there's no children at all, then it's case 1. If we have both children, then it's case 3. Otherwise, we know it's safe to say that they don't have 0 children, they don't have 2 children, therefore they must have 1 child, and then we can handle it accordingly. So now let's go back and rerun my code. And then you see here, so what we're doing is we're deleting 75 and traversing through the tree. So when we look, we see that 75 is indeed gone from our tree, and it's been replaced with this one where we have 76 and 77. So 76 becomes the new 75 with a left child of 60, a right child of 65, and then so on and so forth with 80, 77, 85, and 100. This is the appropriate tree structure, which is great. So there we go. We've essentially handled every single situation inside of deleting, I believe, except for the root case. If we delete the root, I'm not sure if I've tested that one yet. I wonder if that's going to work or not. That's an interesting scenario. Although I believe it should. It should just say, okay, in this case, the 50, it will go and traverse down the right-hand side. So in this case, it will choose... it'll go down the right-hand side, which is 75 is the right-hand side. And then it will find 60, I believe. And I believe it should make 60 the new root. Okay? So we'll see what happens. Let's delete 50 and see if that works. Let's rerun. Yeah, we get a null pointer exception in case 3. So that's interesting. I think there's that one case where we didn't appropriately account for issues. So where is it that it's hitting the issue? with parent left child. It does correctly identify it as a case 3. Well, let's see. Let's go in. Might as well go through and debug and see what the heck is going on. And this time I'll show you what's going on. And we can do it together, and then we should be done this video. So let's see. We searched for node 50. We found it, so it finds node 50. That's great. It should say, yeah, it should say no, that it definitely has both children. So then it goes into case 3, fair enough, which is in here, and I'll put a breakpoint. So it goes into case 3, and it tries to identify the minimum node, which in this case is 60, which is correct. And it invokes a case 2 delete on min node, which is correct because it only has one child. Min node has a right child of 65. Fair enough. Boom, it deletes. So it goes into case 2. Is that where the error was? I forget now. And we say, so node to be deleted is 60 at this point, and the right child is 65. So node to be deleted's parent's left child. Node to be deleted's parents. So the parent of 60 is 75, which I believe is correct. And the left child of 75 is 60, which is correct. So therefore, it's saying the left child should be equal to the right child. So node to be deleted's right child is 65. Okie dokie. So we come out of there. So now we have a tree structure where we have deleted node 60, and I believe we've made the node 75, which is the one we want to delete. We've assigned a left node to it. Let me see. 70, not 60. How do I get to 75? Node to be deleted is 50. Right child is 75. It should now have a left child of 65. That's correct. Cool. That's what we want. So now we take the node to be deleted, which is the root, and we assign everything to the min node. So now the min node, which is now 60, has a left child of 25, which was what the original root had, so that's good. And the right child is 75, which I believe is okay for now. Is that true? Should it be 75? Yes, I think that is correct. So then it says, node to be deleted's parent's left child. Ah, that's the problem, because the node to be deleted's parent doesn't exist, right? Because if we're talking about the root. So the root doesn't have a parent. So is there anything that we can do in this case to appropriately fix this scenario? So if we're deleting the root to be, which is 50, then there is no parent that we need to assign, right? So there's no parent that we need to look at to assign. All we need to do is essentially say that the root is now equal to the min node. So I guess that's what we could say. We could say if node to be deleted dot parent equals null, then this is a special case where we know we're looking at the root. So then we can just say, would that make sense to assign root? Because we've done all of this stuff. Yeah, maybe we could say root is equal to min node, right? Now, does the min node have access to, yeah, because now it has everything through its left child and everything through its right child. I believe that should solve our problem. And we could say else, because we don't want anything to happen, any more deleting or shuffling around to happen or anything, because we don't want to check the parent because we've already done our due diligence here with the root. Okay, so there we go. Let me go back and let me rerun that code and see what happens. Run as, and there we go. So now we have 60 at the root, 25 and 10 and 1 and 30, blah 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 blah, 75. There we go. So I think that we have successfully completed our deletion algorithm. So there you go. Took a little while, but I think it was well worth it. Hopefully you got a lot out of this video and at least understood the finer points of adding, finding, and deleting in a binary tree structure, or rather a binary search tree structure. There you have it. We do our best to help you guys out with your homework assignments with these very long walkthrough videos. So take care of yourselves and have a great day.